Good morning everyone. In today's session we are going to discuss about point processing in image processing. So before that we should understand what is point processing. So point processing is nothing but taking an input image and do some modification over each and every individual pixel to get the transformed form, that is called output image. Okay, so what we are doing here is we are modifying each and every pixel values in order to get the transformed form for the output image. So generally we use f of x comma y to represent the input image. So this is the input image representation. In this image we have number of pixel values. So we are taking each and every pixel values and do some process over it, and finally we will get the transformed form, that is called the output image. So that is represented as g of x comma y. Okay, so this relationship can be represented using the formula S is equal to T of R. Okay, so here S means that the output pixel value. So this output pixel value we are getting only by modifying the input pixel R. Okay, so this R is a input pixel value and S is a output pixel value. So as I told you earlier, in point processing we are taking each and every individual pixels in input image and do some transformation function to get the output pixel. So S is the output pixel. How we are getting? We are doing some transformation function. T is a transformation function or point operation. So by doing transformation function over the input pixel we are getting S. So the relationship between says that S is equal to T of R. Clear? So now we can see one image matrix. It's a 4x4 image matrix. The values are 4, 3, 5, 2, 3, 6, 4, 6, 2, 2, 6, 5, 7, 6, 4, 1. Okay. So this is an input image f of x comma y. Okay. So in this image, see totally 4x4, 16 intensity values are there. So here 7 is the maximum value. So from this maximum value, we can able to calculate the size of the image. Okay. So if you are representing the same intensity values in the form of 2's power, we can calculate the image size. Okay. So the value of this matrix ranges from 0 to 7. So the maximum value here is 7. So the intensity value of this image matrix ranges from 0 to 7. Okay. Now we can write all these values in to the power of 2. 2 power 0 equal to 1. Then 2 power 1 is 2. And 2 power 2 is 4. 2 power 3 is 8. So we can stop up to 2 power 3 is equal to 8 because the maximum value here is 7. So this value lies in between 4 and 8. So we can prefer this relation because 7 is very closer to this 8 and also 7 is lesser than 8. Okay. So in this relation, the power value means that the size of the image. So the size of this image matrix is 3 bits and this 8 is called L value. Okay. So we will use this L value in the upcoming relation. Okay. So clear? So we are considering one image matrix with size 4x4, and from this 4x4 matrix we are calculating the size of the image. So we are writing all these intensity values in the power of 2, and finally we are selecting 2 power 3 equal to 8 relation. From that 3 is the size of the image and 8 is the L value. Okay. Now we can see the types of point processing. First one is digital negative. So if you are having an input image, if you want to take the negation form or negative form of the image, we can use this technique. So this is a kind of point processing technique. So here the formula is S is equal to L minus 1 minus R. So we know what is S and what is R. So S is a pixel value of output image and R is a pixel value of input image. Okay. Now we know what is L. So we can calculate L if you know the maximum value of maximum intensity value of the image matrix. Okay. So consider the same matrix again. F of x comma y 4 3 5 2 3 6 4 6 2 2 6 5 and 7 6 4 1. So using this relation, we are going to get the transformed form of original image f of x comma y. So your input image is f of x comma y. We are going to get g of x comma y. That is the output image by doing this calculation. S is equal to L minus 1 minus R. So in the previous session, I told you for the same image matrix L minus 1, we have calculated L value as 8. So L minus 1 is equal to 7. Okay. Now the range of this matrix is 0 to 7. Intensity range of this matrix is 0 to 7. So if R value is 0, then what will be the S value? If R value is 0, then S value is L minus 1 minus R. Okay, so L minus 1 is 7. 7 minus 0, that is 7. And if R value is 1, then S value is 7 minus 1, that is 6. And so on. R is equal to 2, then S is equal to 7 minus 2, that is 5. Then R equal to 3, S is equal to 7 minus 3, that is 4. If R equal to 4, then S is equal to 7 minus 4, that is 3. If R is equal to 5, S is equal to 7 minus 5, that is 2. If R is equal to 6, then S is equal to 7 minus 6, that is 1. If R is equal to 7, S is equal to 7 minus 7, that is 0. Okay. Now, from this relation, we can form the output matrix G of x comma y. So you can witness we are doing modification over each and every individual pixels in the input image matrix. Okay, so 4. If R is 4, then S value is 3. If R is 3, S value is 4. See the table. If R is 5, S value is 2. If R is 2, S value is 5. Then if R value is 3, then S value is 4. If R is 6, then S value is 1. Then 4, 3, then 6 will become 1. 2, it will become 5. Again 2, it will become 5. 6, 1, 5, 2. And 7, 0, 6, 1, then 4, 3, 7, 6. Okay, so this is your modified output image. Okay, so for the input image matrix, we got the transformed output image G of x comma y. So this is about digital negative. Okay, so for your understanding, we can see one more example. Find the image negation for a 5-bit image of size 5 cross 5 where the border values are 17 and sender values are 7. Okay. So find the image negative for 5-bit image of size 5 cross 5 where the border values are 17 and sender values are 7. Okay. Now we can form the input image. Okay. So the image matrix for the input image is f of x comma y is equal to, so in the problem statement they have mentioned it's a 5 cross 5 matrix and the border values are 17. Okay, so put 5 cross 5 matrix with border values 17 first. 17, 17, 17 and 17. So all the border values are 17 and the sender values are 7. Okay, so the sender values are 7. Okay, now this is an input matrix for the given statement. So the given statement is size of the image is 5 bits and the image size is 5 cross 5 where the border values are 17 and the sender values are 7. Okay, so if you know the size of the image, you can find L value, right? The previous session, I told you how to calculate the size of the image and from that we can calculate the L value. Here, the size of the image is directly given in the statement. So, 2 power 5. So, 5 is the size of the image is equal to 32. Okay. So, we are taking this relation to find the L value. So, in digital negative, we need L minus 1 value. L minus 1 value because the relation is S is equal to L minus 1 minus R. Okay. So, if you know L value, we can calculate L minus 1. So, L value is 32 here and L minus 1 value is 31. Okay. So, how can you find the transformed output image? Here only two intensity values are there, 17 and 7. Okay, we no need to calculate one by one because only two values are there. So the relation is S is equal to L minus 1 minus R. Okay, so here the R values are 7 and 17. Okay, if R value is 17, then S value is 31 minus 17. Okay, and if R value is 7, then S is equal to 31 minus 7. Okay, so this is 14 and this is 24. Okay, so in the modified or output image matrix, what will be the result? G of x comma y is equal to, so instead of 17, what we have to write? 14 and instead of 7 we have to write 24. Okay. Okay, so for this input matrix, we got the modified output matrix using the formula S is equal to L minus 1 minus R. Okay, so this is a concept of digital negative. So in digital negative, we are modifying the input image into the negative form. Okay, so second method is thresholding. So in thresholding, we use the formula S is equal to L minus 1 if R is greater than or equal to, we can fix the threshold value. Based on the threshold value, we are going to modify the input image into output image form. Okay, so here for this example, I am going to fix the threshold value as 4 because we are going to consider the same previous image matrix. So the maximum value here is 7. So I am taking 4 as a threshold value. So the formula here is S is equal to 4 minus 1 if R greater than or equal to 4, and it is 0 if R is less than 4. Okay, so take the same relation 4, 3, 5, 2 and 3, 6, 4, 6, 2, 2, 6, 5, 7, 6, 4, 1. Okay, so we no need to calculate the L value again and again because already in the previous example we calculated the L value. So L value is 8 and L minus 1 is 7. Okay, remember L minus 1 for this matrix is 7. Okay, so the the relation of thresholding says that S is equal to L minus 1 in case of R greater than or equal to 4. If R less than 4, the value will become 0. Okay, so the value ranges from 0 to 7. Okay, so if R values are greater than or equal to 4, that means 4, 5, 6 and 7. If R values are 4, 5, 6, 7, then S value will be L minus 1. So in case of this example, S value is 7. Otherwise, if R is less than 4, that is 0, 1, 2, 3, then S value will become 0. So this is a simple relation for thresholding. Okay, so based on this relation, we can generate the output image g of x comma y. So g of x comma y here is, so 4 is greater than or equal to condition. So 4 is greater than or equal to R. So the value is 4 minus 1 will become 7. Okay. So 3 is less than 4. So this value will become 0. And again 5 greater than 4, 7. Then 2 less than 4, 0. And again 3 less than 4, 0. Then 6 greater than 4, 7. 4 greater than or equal to 4. So that is 7 again. 6 greater than 4, again 7. And next values 2 and 2 both are lesser than 4. So this will become 0. 6 and 5 greater than 4, 7, 7. And 7, 6, 4 greater than or equal to 4. So 7, 7, 7. Finally 1 less than 4. So this will become 0. Okay. So for this input, we got the modified form of output g of x comma y with the matrix, this one, 4 cross 1, 4 cross 4 matrix. Okay. So the next type is clipping. Here we use the formula S is equal to 4 minus 1, 2 less than or equal to R less than or equal to 5. So the value ranges from 2 to 5. If the R value ranges from 2 to 5, the value of S is L minus 1, otherwise 0. Okay. So clipping is also a type of point processing. Here also what we are doing is we are doing some modification over the input pixel values of input image, and finally we will get the modified output image. Okay, so the relation here is S is equal to L minus 1, and if R value ranges from 2 to 5, otherwise 0. Okay, so if you take the same example, so the value ranges from 2 to 5. That is, if R is equal to 2, 3, 4 and 5, then S value will become 7. And for all the remaining values, that is, if R is equal to 0, 1, 6, 7, for all the remaining values, S value will be 0. Okay, so simple relation, if R lies in between 2 and 5, then the S value will become L minus 1. For all the remaining values, that is 0, 1, 6, 7, S value will be 0. Okay, so take the same matrix. Four, 3, 5, 2, 3, 6, 4, 6, 2, 2, 6, 5, and 7, 6, 4, 1. So it's a f of x comma y input matrix, and g of x comma y, that is the modified output images. We can relate this condition. So if R value lies in between 2 to 5, then S value will be 7. Okay, so first value is 4, lies between 2 to 5, then second 7, again 5 is also 7, 2 is also 7. Third relation, value 3, it lies in between 2 to 5, so again 7, 6, it is out of the range, so this value will become 0. 4 is in the range, so 7. 6 is out of the range, so it will become 0. And next 2, 2, again it is in the range, 7, 7. 6 is out of the range, 0. And 5 is in the range, so write 7 here. And the last row, 7 is out of the range, so 0. And 6 out of the range, 0. Then 4 is in between the range, so 7. 1 is out of the range, so write 0. Okay, so for this input matrix, the modified form of output matrix is this one. Okay, so this is called clipping operations. Okay, so in clipping, basic thing is we use the formula S is equal to L minus 1 if R lies in between 2 to 5, otherwise 0. By using this relation, we can form the output matrix. Okay, so finally, we are going to see bit plane slicing. So bit plane slicing, so it's a kind of point processing. Here what we are doing is we are transforming this digital image into a number of binary images. Okay, so the process of converting digital image into number of binary images is called bit slicing. Okay, so we can see how it performs. Okay, so here we use the relation. So take the same example, 4, 3, 5, 2, 3, 6, 4, 6, 2, 2, 6, 5, 7, 6, 4, 1. Okay, so for your understanding, I am writing the same example again and again. F of x comma y, this is the input matrix. So here to convert this digital into binary form, first we have to calculate the number of pixels. Okay, so number of pixels already I have told you how to calculate the size of the image. We have taken the relation 2 power 3 equal to 8. Okay, so the power value says that number of bits in the image. Okay, so 3-bit image is the given matrix. Okay, now we can convert the given intensity values into binary, 3-bit binary values. Okay, so for L, how will you write the 3-bit value? 1 0 0 and 3 0 1 1, 5 1 0 1, 2 0 1 0, and 3 is again 0 1 1, 6 is 1 1 0, 4 1 0 0, again 6 1 1 0, 2 0 1 0 0 1 0, 6 1 1 0, 5 1 0 1, then 7 1 1 0, sorry 1 1 1, 6 1 1 0, 4 1 0 0, and finally 1 0 0 1. Okay. So I already told you in bit plane slicing, what we are doing, we are taking the digital image and converting it into binary form, number of binary images. Okay, so here the most significant bit, center bit, and least significant bit separately considered as 3 different binary images. Okay, so by dividing these 3 bits separately, we will get 3 different binary images. So if you consider the most significant bit, MSB, so you will get 1 0 1 0, 1 0 1 0, then 0 1 1 1, 0 0 1 1, 1 1 1 0. This is a separate binary image, and if you consider center pixel, center bit, so you will get one more binary form, 0 1 0 1 and 1 1 0 1, 1 1 1 0, finally 1 1 0 0. And the least significant bit, that is the leftmost bit. If you consider the leftmost bit separately, you will get the separate binary form. Okay, so 0 1 1 0, and again 1 0 0 0, 0 0 0 1, and 1 0 0 1. Okay, so the process of dividing a digital image into number of binary image is called bit plane slicing. So in bit plane slicing, in this example, the size of the image is 3 bits. So we are converting the given intensity values into 3-bit values first. Then separately, we are separating most significant bit, center bit, and least significant bit to get separate binary images. Okay. So we can review point processing. So under point processing, we have seen the relation S is equal to T of R. S is equal to T of R. Okay. So based on this relation, we have seen 4 different methods. First one is digital negative. So here we use the relation S is equal to L minus 1 minus R, and second one is thresholding method. Okay. So in thresholding method, what we have done is S is equal to L minus 1 if R is less than or equal to 4. Sorry, R is greater than or equal to 4, then 0 otherwise. And third method is clipping. So here we have used the method relation called S is equal to L minus 1 if R value lies in between 2 to 4 or 2 to 5. We can fix the value, and 0 otherwise. And finally, we have seen bit plane slicing. in that method, we have to convert the digital form into binary form to get bit plane slicing. So first we have to calculate the number of pixels used in the image processing. Based on that, we can get number of binary images. Okay, so now we can move on to the image processing, image enhancement technique. So image enhancement is subdivided into three important domains. First one is spatial domain. Temporal domain or frequency domain. You can say frequency domain. And finally, combined so in the first domain, we are dealing with each and every individual pixel transformation, and in frequency domain, what we are doing is to enhance the image, we are doing some Fourier transformation over the overall image. And the third method, that is combination domain, which uses both spatial and frequency domain. Okay, so here we are manipulating the individual pixels. Here we use the Fourier transformation over the whole image. And here we use both domains. Okay, so that is, we will do individual pixel manipulation, as well as we will modify the whole image by using the Fourier transformation. Okay, so under spatial domain, we have important image enhancement technique called histogram equalization. We are going to see it now. So before that, what is image enhancement? So image enhancement is a way of modifying or enhancing the features of one image so that it can be suitable for one particular application better than the original image. Okay, so when we use image enhancement, if you want to modify the features or quality of the image to fit into some application that will be better than the original image, that case we will do image enhancement technique. Okay, so under that image enhancement, we have seen three domains. First one is spatial, second one is frequency domain, third one is the combined domain. So as I told you earlier, spatial domain, here we will manipulate each and every individual pixels to get the modified form. And the second one is frequency domain. Here we use the Fourier transformation methods to modify the overall frequency or intensity values of the input image. And finally, combined domain, which uses both spatial and frequency domain features. Okay, then under spatial domain, one of the important image enhancement techniques called histogram equalization. So we are going to see histogram equalization with one example so that you can understand clearly. First of all, we are going to see one problem under histogram equalization method. Perform the histogram equalization for an 8x8 image shown below. So the data given is in the table. So gray level, that is the intensity value of each and every pixel and number of pixels. So number of pixels is a number of occurrence of this gray level value in an image. Okay. So the given values are 0, 1, 2, 3, 4, 5, 6 and 7. So the number of occurrence of the intensity value 0 is 9. 9 times it occurs in the image matrix, and 1 it occurs 8 times, 2, 11, 3, 4, 4, 10 and 5, 15, 6, 4 and 7, 3. Okay, so this is a given table. So for that we are going to perform the histogram equalization for the given data. So this is in the problem statement they have mentioned it's a 8x8 image. So these are the intensity values in the 8x8 image, 0 to 7. The values ranges from 0 to 7. So the number of occurrence of each intensity values is given in the table, that is number of pixels 9, 8, 11, 4, 10, 15, 4, 3. Okay, so here what we are doing is we are modifying this given input image into output image. So this is also a kind of point processing technique, but here we are taking the input and applying some mathematical calculation over it to get the modified form, that is g of x comma y. So first, for the given input image, we can draw the histogram chart. Okay, so we can consider gray level as x-axis value, and number of pixels is a y-axis value. Okay, so the gray level values varies from 0 to 7. So 0 to 7, right? 0, 1, 2, 3, 4, 5, 6, 7. And number of pixels are 9 to 15. The value ranges from 9 to 15. Sorry, 3 to 15. So the least value is 3 and the highest value is 15. Okay, so if the gray level value is 0 and the number of frequency is 9, how can you represent 0 and 9? Okay, so first plot 3, 4, 5, 6, 7, 8, 9, 10, 11, then up to 15, 12, 13, 14, 15. Now 0 x-axis and y value is 9. So mark it here. And for the intensity value 1, number of occurrence is 8. So mark it here. And for the intensity value 2, the number of occurrence is 11. And for the intensity value 3, the number of occurrence of intensity value 3 is 4. Finally, for 4, the number of occurrence is 10. then 5, 15, 6, 4, and 7, 3. So this is a histogram of given input image. Okay. So now we are going to do histogram equalization. Finally, we will get the modified histogram for the output image. Okay. So the histogram equalization, which involves 4 important steps. First, we have to calculate the PDF, that is probability distribution function. Second, we have to calculate cumulative distribution function. And finally, we have to calculate the value multiplied by the maximum number of intensity value. And finally, we can take the round of value. So we can see it using the table. So for the given input, we are going to calculate the histogram equalization. Okay. So first write the gray level and number of pixels in the table. Zero, 1, 2, 3, 4, 5, 6 and 7. And number of pixels So number of pixels is the number of occurrence of this intensity value in the given input matrix. Okay, so this is represented as n of k. Okay, so number of pixel is represented as n of k. Here the values are 9, 8, 11, 4, 10, 15, 4, 3. So as I told you, in histogram equalization, first we have to compute PDF. So what is PDF? So PDF is a probability distribution function. Okay. So this PDF can be calculated. This PDF can be calculated using the formula nk divided by n. So you know what is nk. Nk is the number of pixel. And what is n? N is the total number of pixels in the image matrix. So if you add these values, you will get 64. Okay. So if you add all these values, 9 plus 8 plus 11 plus 4 plus 10 plus 15 plus 4 plus 3, you will get 64. Okay. So we can calculate probability distribution function using the formula nk by n. So this is nk value. If you divide this value by 64, you will get PDF value. Okay. So first 9 divided by 64, you will get 0.141. And second value 8 divided by 64, you will get 0.125. And third one 11 divided by 64, you can use calculator. 11 divided by 64, you will get 0.172. And similarly, if you divide all these values by 64, you will get these values: 0.0625, 0.156, 0.1234, then 0.0625, and finally 0.047. So we don't want this table because we know the value of gray level and number of pixels. Okay. So first we have calculated the probability density function. Then now we can calculate cumulative density function. So this cumulative density function can be represented using the symbol S of k. Okay. So the gray level values are given in the table. In the problem statement, they have given the gray level. The number of pixels are given. First, we are calculating the probability density function. Then again we are calculating the cumulative density function that is represented as S of k. So the cumulative density function can be calculated. First what we are doing is we are writing the same value here. So for the first pixel level, so for the first pixel value, we are taking the same value as a cumulative value, that is 0.141. But for the next one, what we are doing is we are adding this value with the PDF value of gray level. So 0.141 is added with 0.125. You will get the new cumulative CDF, cumulative density value. Okay. So here we will get 0.266. What we have done is, first I have taken the same value here. PDF of first gray level is taken as the CDF of first gray level, and for the successive values, what we are doing is we are cumulatively adding the previous value. Okay, so this value is added with the next gray level PDF and you will get the new value. Then again this value is added with the next value, that is 0.266 is added with 0.172, you will get 0.438, and again add 0.438 with this value, you will get 0.5005. Again add this value with the previous value, that is 0.156 is added with 0.5005, you will get 0.6565, and again add this value with previous cumulative value 0.6565, you will get 0.8905. Again add this value with the previous cumulative value, you will get 0.953. Finally, if you add these two values, you are getting 1 as a result. Okay, so we have calculated the cumulative probability density function. Okay, so next step is we have to multiply this Sk with 7. Okay, so what is 7? What is 7 here? So already I have told you how to calculate the L value, right? So here L means 7 means that L minus 1. So first we have to calculate the L value. How will you calculate L value? First we have to write all the intensity values in the form of 2's power. So here also we use the intensity values which ranges from 0 to 7. So if you write all these values in 2's power, 2 power 0 is equal to 1, 2 power 1 is equal to 2, 2 power 2 is equal to 4, and 2 power 3 is equal to 5. Sorry, 2 power 3 is equal to 8. So the maximum intensity value here is 7. So 7 is very closer to 8 and lesser than 8. So I am taking this relation. So in this relation, 3 is the number of pixels in the input image and 8 is the L value. So if 8 is L value, then L minus 1 is 7. Okay. So here the formula is Sk multiplied by L minus 1. Okay. So Sk value is cumulative distribution function. So multiply this value with 7, you will get you will get this column values. So 0.147 is multiplied with 7, you will get 0.987. Similarly, multiply all these values with 7, you will get the following values: 1.867, 3.066, then 3.5035, 4.5955, then 6.233, then 6.671, finally 7. So in the last column, we are going to find the histogram equalization of given grayscale level. Okay. So the histogram equalization for the given gray level is calculated by taking the round off value. So 0.987, so the round off value is 1. Here 1.8, it will become 2. 3.0, that is 3. 3.5, 4. 4.5, 5. Then 6.26, 6.67, and again final value is round off value 7. Okay, so if you take this column 1, 2, 3, 4, 5, 6, 7, 7. So there is a repetition. So for this histogram equalization value, the number of occurrence. So the number of occurrence of 7 is 3 and 4. So the new number of occurrence is 3 plus 4, 7. Okay. So after calculating all these values, so in this what we have done, from the problem statement I have written the gray level, then number of pixels, then I have calculated PDF value. From the PDF value we have calculated the CDF, that is cumulative distribution function. Finally we are multiplying this value with L minus 1 value, we are getting this table, and at the end we are calculating the histogram equalization by taking the round off value of this Sk into L minus 1. Okay, so and if you identify any repetition or duplication, you can add the number of pixels, add the number of occurrence of same gray level value to find the number of occurrence. And now from this table we can draw the histogram table. So here also the pixel level, pixel grayscale value level, gray level, and the number of pixels. Write it here. So the pixel values in the histogram equalization, the pixel values are 1, 2, 3, 4, 5, 6 and 7. 1, 2, 3, 4, 5, 6 and 7. And the number of pixels, that is n of k, is for 1 9, for 2 8, for 3 11, 4 it is 10, for 4 it is 4, for 5 it is 15, and for 6 it is 4. For 9, 8, 11, 4. For 5 it is 10. For 6 it is 15. For 7 we have added 4 and 3. You will get 7 again. Okay. So by using this histogram values, again we can plot the histogram graph. So here also the x-axis represents gray level and y-axis represents number of pixels. So gray level ranges from 1 to 7. And number of pixel ranges from 9 to 15. Sorry, 7 to 15. Up to 15. Okay. So for the gray level 1, the number of pixels are 9. Plot it like this. Then 2, 8. Then for 3, 11. Then for 4, it is again 4. Then for 5, it is 10. For 6, it is 15. And for 7, it is again 7. Okay. So this is a way of converting a given input image into histogram equalization image. Okay, so the histogram equalization, which involves three major steps. First, we have to calculate the PDF. So to calculate the PDF, we should have the number of pixels. So that is nk. From nk, we can calculate n value. That is the total number of pixels in the input image. Okay, so after calculating the PDF value, we can calculate the cumulative distribution function that is represented as S of k. So here the first value, we how we are calculating the CDF, we are taking the same PDF as CDF for the first value. For the all other remaining value, we are taking the previous CDF and add it with the PDF value. We will get the cumulative CDF. Okay. Then the next step, what we are doing is we are taking this SK and multiply with L minus 1 value. So in this example, L minus 1 value is 7. So finally, we will round off all this SK into L minus 1. We will get the histogram equalization.